Welcome to the Deep Dive. Today, we're going on a journey
Ooh, a journey.
through the history of the Central Limit Theorem,
Okay.
or CLT. You've given us some fascinating excerpts from A History of the Central Limit Theorem
By Hans Fischer.
by Hans Fischer. Let's see what hidden gems we can uncover together. Now, I'm no statistician,
Right.
but I get the basic idea.
Yeah.
The CLT tells us that the average of
Okay.
many independent random events tends to form
Yeah.
that familiar bell curve shape,
Okay.
even if the individual events themselves aren't normally distributed. Is
Mhm.
that a decent summary?
Yeah, that's a great starting point. Think of it like this. Imagine you're flipping a coin 100 times.
Mm-hmm.
You wouldn't expect exactly 50 heads and 50 tails every time.
Right,
There'd be
yeah.
some variation.
Yeah.
But if you did this experiment
Okay.
many, many times and averaged the results,
Yeah.
that average would start to resemble a normal distribution, that bell curve you mentioned.
So even though individual coin flips are random, when we zoom out and look at the big picture,
Yeah,
a pattern emerges.
exactly.
That's pretty amazing. But where did this idea even come from? Who started connecting these dots?
Well, our journey begins back in the 1700s
Okay.
with Abraham de Moivre.
Wow.
He was wrestling with the problem of approximating the binomial distribution.
Okay.
You can think of it as
Yeah.
trying to figure out the probabilities of different outcomes in a series of coin flips.
Okay.
Well, he didn't call it the CLT.
Right.
His work laid the groundwork for later discoveries.
So de Moivre was kind of like a trailblazer, forging a path without even knowing exactly where it would lead.
Exactly. And following this path, we encounter Pierre-Simon Laplace
La pause.
in the early 1800s.
Okay.
He took de Moivre's work and really expanded on it,
Uh-huh.
applying it to real-world problems like astronomy and errors in measurement.
Interesting.
In fact, he even wrote a whole book on the subject,
Oh.
Théorie analytique des probabilités. This book wasn't just a collection of formulas.
Right.
It was a landmark achievement that showed how probability could be used to solve practical problems and make scientific inferences.
So Laplace wasn't content with just the theory.
Yeah.
He wanted to see how this new understanding of probability could be applied to the real world.
Exactly.
What was his approach like?
Well, his analytical style evolved over time.
Okay.
Initially, he was heavily influenced by Leonhard Euler's work,
Euler. Okay.
which relied heavily on the use of infinitely small and large quantities.
Right.
But later, he adopted a more algebraic approach, inspired by Joseph Louis Lagrange.
Interesting.
This shift was crucial because it allowed him to tackle more complex problems and develop more rigorous proofs.
It's like he realized he needed sturdier tools to build something truly lasting.
Yeah.
So was the CLT already a fully formed theorem by this point?
Not quite.
Okay.
At this stage, it was more like a collection of problem-solving techniques that Laplace was using to tackle a variety of problems. But even without a formal definition,
Okay.
he was fundamentally changing how people viewed probability. It was becoming a powerful tool for understanding and analyzing data,
Right.
not just a way to calculate odds in games of chance.
That's a pretty big shift in thinking, but I imagine not everyone agreed with Laplace's methods
Oh,
or
absolutely.
his conclusions, right?
Definitely not.
Were there any challenges to his work?
Oh, absolutely. In the early 1800s,
Okay.
Simeon Denis Poisson enters the picture.
Poisson.
He built upon Laplace's work,
Uh-huh.
but also sparked some debates by introducing his own proofs,
Okay.
some of which were a bit flawed.
Oh, interesting.
This kind of back and forth is actually vital in the development of any scientific idea.
So even disagreements can push the field forward.
Absolutely.
It's like constructive criticism.
Yeah.
Sometimes you need someone to point out the flaws in your thinking to help you make it stronger.
Precisely.
Okay.
And that's where Peter Gustav Lejeune Dirichlet comes in.
Sure.
During the 1840s, he brought a much-needed dose of rigor to the field,
Okay.
laying the foundation for modern proofs of the CLT.
Hmm.
One of his key contributions was something called Dirichlet's discontinuity factor.
Okay.
Now, this sounds technical,
Right.
and it is,
Yeah.
but think of it like this.
Okay.
He created a mathematical tool that allowed him to handle situations where the traditional approaches were breaking down. It was like having a special wrench to loosen a stubborn bolt.
So Dirichlet was tightening up the loose ends and
Yeah.
making the CLT more robust.
Exactly.
It sounds like things were getting increasingly sophisticated.
Yes.
What happened next in this mathematical evolution?
Well, around the same time,
Okay.
a fascinating idea began gaining traction:
Okay.
the hypothesis of elementary errors.
Elementary errors. Okay.
This was the notion that errors in observations,
Okay.
like those made by scientists taking measurements,
Right.
arise from many tiny independent sources rather than one big mistake.
So instead of one massive blunder, it's a bunch of small imperfections all adding up.
Exactly.
Kind of like if a recipe goes wrong,
Uh-huh.
it's probably not because you dumped in a whole cup of salt by mistake,
Right.
but because you might have slightly mismeasured a few different ingredients.
That's a great way to put it.
Okay, good.
Carl Friedrich Gauss, who you might know from the Gaussian distribution,
Right, gas.
was a big proponent of this idea.
No.
While he didn't come up with the hypothesis of elementary errors,
Okay.
his work with the normal distribution definitely fueled interest in understanding why errors often followed this bell-shaped curve.
I see. So it's one thing to observe a pattern,
Right.
but quite another to figure out what's causing it.
Exactly.
I guess that's where Hagen comes in.
Exactly. In the 1830s,
Huh.
Gotthilf Hagen
Hagen.
took this idea of elementary errors and applied it directly to the Gaussian curve.
Hmm.
He argued that if you have a bunch of tiny, equally likely errors,
Hmm.
they'll combine to create the bell shape of the normal distribution.
Oh, interesting.
He even wrote a book about it called Essential Features of Probability Calculus.
Okay.
Now, his proof wasn't completely perfect,
Right.
and some of his readers struggled with the concepts of infinity and infinitesimals,
Yeah.
which were pretty mind-boggling at the time.
Those concepts can definitely be a bit tricky to wrap your head around.
Right.
It's like trying to imagine the edge of the universe.
Yeah.
It's so vast, it almost defies comprehension.
Exactly.
Yeah.
And that's why Friedrich Wilhelm Bessel's work was so important.
Bessel. Okay.
In 1838, he generalized the hypothesis of elementary errors,
Okay.
saying that these tiny errors don't have to be all the same size or have the same probability.
Okay.
This made the hypothesis much more applicable to real-world scenarios where errors are rarely uniform.
So Bessel was adding more nuance to the picture,
Exactly.
recognizing that errors in the real world are often messy and unpredictable.
Precisely. But here's where things take a really interesting turn.
Oh, a turn.
Adolf Quetelet,
Catille.
a Belgian statistician and astronomer,
Okay.
took this idea of elementary errors, which was initially used to understand measurement errors in science,
Right.
and applied it to biology and social sciences.
Okay.
He started looking at things like the heights of people in a population
Okay.
and noticed that they also tended to follow a normal distribution.
Wait, so he's saying that variations in human characteristics like height might also be explained by lots of small underlying factors.
That's exactly
That's
that.
a pretty bold leap.
It was a huge leap.
Yeah.
And Quetel's work was groundbreaking because it showed that the normal distribution,
Okay.
and by extension the CLT,
Right.
had implications far beyond the realm of measurement errors.
Okay.
It could be used to understand variations in the natural world and even in human societies.
Wow, this is blowing my mind. We've gone from coin flips to astronomy to errors in measurement to the very shape of human society.
Yeah.
It's incredible to see how these ideas have evolved and expanded over time,
Yeah,
but I'm guessing this isn't the end of the story.
definitely not. There's much more ground to cover.
All right.
We need to travel to Russia and explore the contributions of Pafnuty Chebyshev and Andrei Markov,
Ooh, Russia. Exciting.
the mathematicians who truly elevated the CLT to its status as a core mathematical theorem.
Okay.
But we'll save that adventure for the next part of our deep dive.
I'm ready for that adventure. Let's go to Russia.
All right, so let's fast forward to late 19th century Russia.
Okay, Russia.
This is where we meet two figures who revolutionized our understanding of the CLT,
Okay.
Pafnuty Chebyshev and his student Andrei Markov.
Chebyshev and Markov. Okay.
What they brought to the table was a new level of rigor
Okay.
and abstraction.
Right.
They weren't just solving specific problems. They were building a whole new framework for understanding probability.
So instead of focusing on individual applications,
Yeah.
they were looking for the underlying principles that govern the behavior of random events.
Exactly.
It's kind of like how early astronomers might have been focused on charting the positions of stars and planets. But then along came Kepler and Newton,
Right.
who developed laws to explain why those celestial bodies moved the way they did.
That's a great analogy.
Yeah. Okay, cool.
Chebyshev was especially fascinated by something called moment theory.
Moment theory. All right.
Now, moments might sound a bit abstract,
Yeah.
but they're really just a way to describe the shape of a probability distribution.
Okay.
Think of it like this.
Okay.
The first moment tells you about the average or the center of the distribution,
Okay.
while the second moment tells you about the spread or the variability.
So moments give you a way to capture the essence of a distribution without getting bogged down in all the specific details.
Exactly.
Okay, cool.
But how did this help him with the CLT?
Yeah, how did it?
Well, Chebyshev realized that you could use these moments to prove the CLT
Okay.
in a much more general way.
Right.
Instead of relying on specific formulas for different distributions,
Yeah.
he could use these general properties of moments
Right.
to show that under certain conditions,
Oh.
the average of independent random variables would always tend towards a normal distribution.
That's pretty powerful.
Yeah.
He was finding a way to unify these seemingly disparate ideas under one overarching theory.
Exactly.
And I imagine his student Markov continued down this path of abstraction.
Absolutely. Markov not only refined Chebyshev's ideas,
Okay.
but also applied them to specific cases of the CLT.
Mm-hmm.
But what's really fascinating
Yeah.
is that his work went far beyond the CLT.
Okay.
He developed a whole new branch of probability theory
Wow.
called Markov chains,
Markov chains. Okay.
which have become incredibly important in fields ranging from physics and computer science to finance and even linguistics.
Markov chains, that rings a bell. I vaguely remember learning about them in a college math class.
Right.
It has something to do with systems that transition between different states.
Exactly. Imagine you have a system that can be in one of several states,
Okay.
say sunny, cloudy, or rainy.
Mm-hmm.
A Markov chain describes how the system transitions between these states, where the probability of moving to a new state depends only on the current state,
Okay.
not on the entire history of the system.
So it's like a weather forecasting model where today's weather influences the probability of tomorrow's weather,
Yeah,
but yesterday's weather is irrelevant.
precisely. And Markov chains are incredibly versatile.
Okay.
They can be used to model all sorts of things, from the behavior of stock prices to the spread of diseases to the evolution of language.
Wow. So from the CLT to Markov chains.
Yeah.
It seems like Chebyshev and Markov really opened up a whole new way of thinking about probability and random processes.
It's true.
But I'm guessing the story doesn't end there.
You're absolutely right.
Okay.
The beauty of mathematics is that it's a constantly evolving field,
Right.
with each generation building upon the work of those who came before.
Yeah.
The CLT is no exception.
Okay.
As we move into the 20th century,
Mm-hmm.
we'll see how mathematicians continue to refine and generalize the CLT,
Okay.
pushing its boundaries further and further.
So while Chebyshev and Markov laid the foundation,
They did.
there were still more stories to be told.
Absolutely.
More connections to be made. This is getting exciting. Who are some of the key players in this next chapter of the CLT saga?
Well, there were several mathematicians who made crucial contributions,
Okay.
but two names you absolutely need to know
Okay, hit me.
are Alexander Lyapunov and Paul Levy.
Lyapunov and Levy. Okay.
They brought a whole new level of sophistication to the CLT,
All right.
pushing it into the realm of modern probability theory.
Sophistication is good, right? I'm ready for another mind-blowing leap forward. What made their work so groundbreaking?
Well, Lyapunov in 1901 came up with a proof of the CLT that was much more general than anything that had come before.
Okay.
He relaxed some of the earlier conditions required for the CLT to hold,
Right.
which meant it could be applied to a wider range of random variables.
Okay.
In the world of mathematics, making a theorem more general is a huge deal
Right?
because it means it becomes a more powerful tool, applicable to a greater variety of problems.
It's like having a universal remote that works with not just your TV, but all your electronic devices.
Yeah.
Much more useful.
Exactly.
Good, good, good.
What about Levy? What were his contributions?
Yeah, what about Levy?
Levy, working independently around the same time as Lyapunov,
Uh-huh.
was also exploring new territory.
Okay.
He was particularly interested in something called characteristic functions,
Characteristic functions. Okay.
which are a powerful tool for analyzing probability distributions.
Okay.
You can think of them as a sort of mathematical fingerprint
Okay.
that uniquely identifies a particular distribution.
So each probability distribution has its own unique signature.
Yeah,
Like a musical chord has its own distinct sound.
precisely.
That's pretty neat. But how did this relate to the CLT?
Well, Levy's work with characteristic functions
Yeah.
allowed him to develop new and more elegant proofs of the
Yeah.
CLT.
Okay.
He also made significant contributions to our understanding of how the CLT connects to other areas of probability theory. It's like
Right.
the study of infinitely divisible distributions.
Hold on. infinitely divisible distributions. That sounds pretty intense. What exactly are those?
Imagine you have a cake,
Okay, cake.
and you can keep cutting it into smaller and smaller pieces,
Yeah,
no matter how tiny you want those pieces to be.
right.
An infinitely divisible distribution is kind of like that.
Okay.
You can keep dividing it into smaller and smaller distributions without changing its fundamental nature.
Hmm.
It turns out that the normal distribution,
Right.
the one that pops up all the time with the CLT,
Yeah.
is a prime example of an infinitely divisible distribution.
Wow, I never thought about the normal distribution like that. So Levy was exploring the connections between the CLT and these more abstract mathematical objects.
Exactly.
It seems like he was pushing the boundaries of probability theory.
He was, and both Lyapunov and Levy, through their work,
Yeah.
helped to solidify the CLT as a central pillar of modern probability theory.
Okay.
It was no longer just a handy tool for solving specific problems. It was becoming a fundamental concept in its own right.
So from its humble beginnings with coin flips and games of chance, the CLT had risen to the ranks of a mathematical superstar. What a journey.
It certainly has. But the story doesn't end there.
Oh, there's more.
The CLT continued to evolve throughout the 20th century and beyond,
Wow.
inspiring new discoveries and applications in fields as diverse as physics, finance, and even biology.
I'm sensing there's still more chapters to this fascinating saga.
Oh, there are.
What other twists and turns await us in the world of the CLT?
Well, we still have to explore the work of William Feller,
Colarbell.
Alexander Kinchin,
Kinchin.
and delve into the intriguing connections between the CLT and the mesmerizing world of Brownian motion.
Okay.
But for now,
Okay.
let's take a short pause in our journey and pick up the story in the final part of our deep dive.
All right. I'm ready for that final part. Let's do it. Okay, so we've journeyed from the early pioneers, like Demoivre and Laplace, through the rigor of Chebyshev and Markov and into the 20th century with Lyapunov and Levy. I'm ready for the next leg of this mathematical adventure. Who else shaped the CLT as we know it today?
Well, there were many contributors, but let's start with William Feller.
Feller.
He was a leading figure in probability theory in the mid-20th century.
Mm-hmm.
One of his key achievements was to nail down the necessary conditions for the CLT. It's one thing to say, hey, under these conditions, the CLT works.
Right.
But Feller wanted to know, what are the absolute must-haves, the non-negotiables for this theorem to hold true?
So he was drawing those hard lines in the sand, saying, if you cross this, the CLT is off the table. What kind of conditions are we talking about here?
We're getting into some technical details, but essentially, Feller was digging deep into the properties of the individual random variables that are being averaged. He wanted to know how their individual distributions and how they interact affect whether or not the CLT applies. His work was crucial because it gave a more complete picture of the CLT's reach and its limitations.
So not just expanding its applications, but also understanding its boundaries. That makes sense. Where does Alexander Kinchin fit into all of this?
Kinchin, another brilliant mind of the 20th century, dove deep into the fascinating world of infinitely divisible distributions. Remember our cake analogy?
The cake, yeah.
The idea that you can keep dividing it into smaller and smaller slices without changing its fundamental essence. He was particularly interested in the connection between these infinitely divisible distributions and the CLT.
Now, you mentioned that the normal distribution is a prime example of an infinitely divisible distribution. Did Kinchin's work shed more light on that connection?
Absolutely.
Yeah.
He helped clarify the relationship between the abstract properties of infinitely divisible distributions and the more concrete results of the CLT. It's like finding a hidden passage that connects two seemingly separate rooms in a vast mansion.
Those hidden mathematical passages always lead to the most exciting discoveries. But speaking of exciting, you mentioned something about the CLT and Brownian motion.
Yes.
That's where things always seem to get a little mind-bending for me.
Brownian motion is one of those concepts that seems chaotic on the surface, but has this deep connection to the CLT.
Okay.
It was named after the botanist Robert Brown, who in the 1820s observed pollen grains jiggling around randomly in water.
Right.
It turns out that this seemingly random motion, when viewed through the lens of the CLT, starts to reveal some underlying order.
Okay, so this random jiggling of pollen has something to do with the bell curve in the CLT. How does that even work?
Well, imagine you zoom in on the path of a single pollen grain and look at its tiny movements over very short intervals. Those little jumps and wiggles, when analyzed statistically, start to look a lot like normally distributed random variables.
So hidden within the chaos of Brownian motion is the order of the normal distribution.
Exactly.
That's pretty remarkable. It reminds me of those impressionist paintings that look like a jumble of colors up close, but then when you step back, you see a beautiful, coherent image.
Exactly. And this connection between the CLT and Brownian motion has had profound implications for a wide range of fields.
Hmm.
It's been used to model everything from stock prices and interest rates in finance to the movement of particles in physics and even the spread of genes in populations.
Wow, the CLT has come a long way from its origins and coin flips and games of chance. It's amazing to see how this seemingly simple idea has branched out to touch so many different areas of science and mathematics.
It truly is. And what's even more remarkable is that the journey is far from over. Mathematicians are still exploring the CLT today, finding new connections, generalizations, and applications. It's a testament to the power of human curiosity and the endless potential of mathematical inquiry.
Well, I think it's safe to say that our deep dive into the CLT has been a resounding success. We've covered centuries of mathematical thought, from the early pioneers to the giants of the 20th century, and we've seen how this one idea has woven its way through a vast tapestry of knowledge.
It's been a pleasure sharing this journey with you.
And to our listeners, we encourage you to keep exploring. Look for the CLT in your own fields of interest, your own daily experiences. You might be surprised at where you find it and how it shapes our understanding of the world. Until next time, happy exploring.